My presentation is called Nanosize Azimuth Layers in New Liquid Crystal Devices. My name is Vladimir Chigrinov. I present Hong Kong University of Science and Technology and Moscow State University and Nanjing Jinsui Optical Technology. I'm a professor in Hong Kong University of Science and Technology. I have many awards, and I am SID fellow, and I have prize. So I have written many books, 6 books in liquid crystals. I'm a mathematician by education, but I was involved in liquid crystal physics for a long time. And I have made about 50 US patents. My Google index is 57 and Web of Index is 43. There are many awards which I showed you here in the picture. And latest awards was SID Award Slotovaki Prize for my educational efforts and supervision and conference organization presentations. Recently, I became a chief of editorial board in liquid crystal section, editor-in-chief in liquid crystal section in Crystal Journal. So in my presentation, I would like to tell you about photoalignment as a new liquid crystal technology. I will tell you about several applications like e-paper, security films, photoaligned ferroelectric liquid crystals, and finally, I will try to tell you about. So you are well aware that usually liquid crystals are made by rubbing. Rubbing means that you make particles, static charge, and mechanical damage. So in principle, you should use photoalignment technology, which is non-contact method with fine resolution. So you don't touch. And then you eliminate electrostatic charges and impurities. You have a controllable tilt angle and anchoring energy. And in principle, you can have new advanced application, fiber communications, and curved and flexible substrates when usual liquid crystal technology is very difficult to apply. You can also manufacture different liquid crystal photonics elements like pattern polarizers, phase retarders, tunable optical filters, lenses with voltage controllable distance. Actually, photoalignment technology first appears in 2009, and company Sharp introduced it. And they were very happy because they have extremely high contrast ratio, high optical efficiency, fast response time, and improved production efficiency when they use photoalignment technology. You can look at this picture. So before TV used defects at the center of the pixel and patterned electrodes, but photoalignment can make angles very, very uniform, and you don't need to make any problems with defects and patterning electrodes. You can look at the picture here, and you can see that bright state is extremely bright, and dark state is much better. This technology is called UV2A technology. UV vertical alignment of liquid crystals made by by photoalignment technology. Here is President Mr. Katayama, President of Sharp University, and he demonstrated Gen 10 on TFT technology photoalignment. And here you will see the picture of TV, which has extremely high color, high resolution, fast response time, and very efficiently produced in Japan. And this is a picture from Hong Kong shop. In 2014, we wrote the book, which is called Photoalignment of Liquid Crystal Materials. We are now working on the revision of. In this book, we showed that photoalignment is nanotechnology, nanolayers, and these nanolayers can effectively align liquid crystals. So the thickness of the nanolayer is about between 1 and 10 nanometers. And one molecule of azo dye can align 10 million more liquid crystal in the bulk. Here you will see very smooth atomic force microscope image of azo dye films, which are very smooth, and the best azo dye which we can use for photoalignment is sulfonic. We also investigate how good this photoalignment, what is the resolution. We registered diffraction plate, diffraction grating, and estimate the resolution by diffraction grating quality. We think that resolution can be better than 75 nanometers. So on the level of the quality of our images, of our optical instrumentations. Azo dye can be effectively align liquid crystals not only on glass, but also on plastic substrates, and key characteristic reflectance, response time, relaxation time are almost the same. Moreover, because you don't need high temperature, which is usually used for rubbing materials, then you can use many different plastic substrates for alignment of liquid crystal on plastic substrates. We demonstrate the photoalignment on plastic substrate of liquid crystal in ATM cards, flexible cards, and we actually even make the line which can make roll-to-roll technology using azo dye photoalignment layers together with our collaborators and chemicals. Let me now a little bit tell you about different applications of azo dye photoalignment for liquid crystal. One application is optically writable paper. So the idea of optically rewritable paper is very simple. You just rotate the molecules of nanosize azo dye layer, and because of steric interactions, the molecule will rotate liquid crystals in the bulk. So in principle, you can change twist angle of liquid crystal. If you change twist angle of liquid crystal, you can change the direction of the polarization, and you can change the image, the gray level. You don't no need to use UV light. You can use blue LED light for 15 nanometers. So you can make image on the computer. You can by RF transfer image to this LCD module, amplitude modulator, and then shine the light, and you will put the picture on the liquid crystal layer. We called it the new types of Xerox. Usual Xerox can be made only one time, and then you throw away the paper, which is not green technology. But here, you can write image and erase 10,000 times. So we consider that a new type of Xerox machine. So here is the images, and here is a picture which shows how to erase the images. As an amplitude modulator, you can use thin film transistor, black and white, with high resolution. So dependent on the light, you can either transfer azo dye to high extent to large angle or instead of amplitude modulator, you can use polarization controllable light printer. So you can, in principle, rotate continuously polarization of the light using the polarizer, liquid crystal cell, and quarter wave plate. If you change the voltage, you change birefringence of the liquid crystal and continuously change the polarization plane rotator. Okay, dependent on the location of the polarizers, you can have bright images on the dark background, or you can dark images on the white background. You can also have many gray levels, and for each gray level, you can record an image. And you can have excellent and very good resolution for our e-paper. So here, resolution by 140 ppi is obtained. In comparison with electronic ink, which usually used for the purpose, for instance, by Top & Company in Japan, our e-paper has extremely high resolution, no TFT array, so it is very cost effective. Color triangle is better than 25% NTSC. High contrast ratio, very wide operation temperature range, and speed at which you can write and erase the image is about 1 second. So it can also be done in flexible, and no issue with ratio. In comparison with cheapest liquid crystals, because our paper has no current conducting layer and has no drivers, it is about 2 times or 3 times cheaper than the cheapest liquid crystal. So, roughly speaking, we can make our paper very durable and flexible, lightweight, good brightness, high contrast ratio, wide viewing angle, low cost, no electrodes, zero power consumption, and display and driving units operated. Now we are working with color filters, trying to make full color paper, and we are working also with flexible paper, trying to show that a paper can be flexible. In principle, if you can write 2 images and put lens array or use glasses, you can have 3D e-paper based on optically rewritable. We demonstrated it, and we demonstrated also the 3D image which can be used in this case. So as I told you, we can make price labels, applications include labels in supermarkets, science and advertising displays outdoor. Definitely you should protect if you in outdoor paper from sunlight, so you should have UV. And definitely it can be other applications. It can be not only price labels in supermarkets. It can be ATM cards labels. It can be badging and conferences. It can be Next, let's go to security films. For security films, because we have very high resolution, it is easy to make security films, and security films will not be seen without special polarizers. So what we are doing, we put azo dye with liquid crystal monomer, then make a picture, polymerized liquid crystal monomer, and then we can full color black and white, high resolution, or even color image. An image can be changed if you rotate the polarizer. So this is new type of security films. And finally, I would like to go to the latest application for our paper is photoaligned ferroelectric liquid crystal. You know that ferroelectric liquid crystal were discovered in 1975 by Bob Mayer. In 1980, Noel Clarke and Sven Lagerbold, they demonstrated first surface stabilized ferroelectric liquid crystal mode. But unfortunately, it was not good, not stable, mechanically unstable. Defects appeared when you have mechanical damage and so on. So since 1989, together with my colleague and friend Martin Schott, we proposed first deformed helix ferroelectric effect, and then together with my colleague Evgeny Pozhidaev and Professor Abhishek Srivastava, we demonstrated many different electro-optical modes based on photoaligned ferroelectric liquid crystals. So roughly speaking, ferroelectric liquid crystal is switchable phase retardation plates because it reacts to, it is linear electro-optical effect. So changing the direction of electric field, you change the direction of phase. But very important for ferroelectric liquid crystal to have optimal anchoring energy. Anchoring energy cannot be smaller, cannot be high, because you align along zero, theta equal to zero, but switch between theta plus minus. So you cannot have small, you cannot have low anchoring. So photoalignment is excellent technology for liquid crystal. There were different electro-optical modes, like deformed helix mode, which can get very fast response time, and similar similar electro-optical response like pneumatic liquid crystal, but response time about 10 times faster. Another electro-optical effect is called electrically suppressed helix mode, which is mode can have extremely fast response time, and this mode can also have very high resolution. Okay, so for ferroelectric liquid crystal, we can use displays, and definitely there are many other electro-optical modes which has fast response time. But ferroelectric liquid crystals not only have fast response time, but can be switched for very small voltages. It means that we can apply special types of micro displays, like CMOS backplanes, which cannot be applied otherwise. Okay, so for ferroelectric liquid crystal, we can have 120 microsecond response time with voltage minus 1 volt per micron. We demonstrated fast response time and voltage in a SID conference in 2018, which is jubilee year for liquid crystal display, 50 years from where first liquid crystal display appeared, and 180 years when liquid crystal come to investigation. The best price in ISO. So here is my team, here is myself, here is my PhD students, and here is Professor Abhishek Srivastava, who is working in this direction. So ferroelectric liquid crystal on silicon has very many good practical application: military, medical, augmented reality, virtual reality, entertainment, and this for AR, VR, they can successfully compete with organic light emitter diodes used for the purpose. Other application of ferroelectric liquid crystals is optical network switch, LiDARs, 3D printing, engineering inspection, 3D face recognition, 3D fingerprint, spectral imaging, medical, and the market growing fast. So you can see that it is several billion US dollars, about 100 billion yuan here. So LiDARs, light switch, processing, and so on. So finally, in summary, I would like to tell you that ISO-dye photoalignment technology is well developed and ready for various applications in display and photonics. Using ISO-dye photoalignment layers, we can develop optically rewritable paper for labels on displays and plastic cards, outdoor advertising products, and so on. And we have also developed security films to protect the papers, to protect the devices, to protect the documents, which has successful application. And then, in summary, we also mentioned fast ferroelectric liquid crystal, which are good candidate for new generation of field sequential color LCD, which proved to be better in response times than pneumatic LCD. We solved many problems already in ferroelectric liquid crystals. By using photoalignment, we demonstrated different types of regimes and different electro-optical modes. And we are now concentrating on making prototypes and arranging mass production of ISO-dye photoaligned ferroelectric liquid crystal devices. So prototypes of ferroelectric liquid crystal devices can be include not only micro displays, but also 2D, 3D displays, and so on. Finally, I would like to tell you many thanks to people whom I work with, in particular my friend and colleague Martin Chad, who is the father of liquid crystal display. Some people in the US, Isaac Hu, ST Wu, and so on. People in Japan, in Poland, Australia, Sweden, and definitely I would like to tell thank you to my colleagues, Hong Kong University of Science and Technology, in particular Professor Kwok and Professor Srivastava. And now I'm trying to continue working with my colleagues in China, with Nanjing University Professor Yan Qinlu and Professor Wai Hu. And definitely I continue working with my Russian colleagues, Vladimir Kozenkov, Viktor Belayev, Denis Chausov, and Alexei Kudreiko. Thank you very much for your very kind attention, and I hope that my presentation was of interest to you.